Now the second order rate equation, the integrated rate equation that I started with in the last video, is a special case where both of the reactants are the same. In this case, however, what if we have, if we're looking for the rate constant, binding a substrate to enzyme? So now both of the reactants are different. And so we can solve for this as well. And what we need to take into account then is the conversion of the enzyme into different complexes. So if this is the initial concentration of enzyme, then at any time t, we're going to have some concentration of enzyme that's not reacted yet, and then amount of enzyme that has substrate bound. Now, very quickly, let's take a second to note that this is not ligand binding. So, in the terms of equilibrium, we're not looking at it solving the equilibrium equation here. What we're looking at is to determine the rate constant. Okay, so this is a different equation entirely than from when we're trying to figure out, for instance, theta, what percentage of the enzyme has substrate bound to it, like we did for the ligand binding equation for hemoglobin or myoglobin. Okay, so the other thing we have to take into account is substrate, and that's going to have its own set of basically a balanced equation here, where the initial concentration of substrate is going to be equal to the amount of substrate still free at any given time plus the amount that is bound to the enzyme. Okay, so in this case we set up our equation where we're going to set this up that instead of looking at the consumption of either E or S, we're going to look at the formation of product. So in this case, the product is the enzyme substrate complex. So we're going to set this equation up to read as DES dt equals plus K, and K is going to be the concentration of free enzyme at any given time times the concentration of S at any given time. And then we have to rearrange this and substitute in, and what that ends up looking like is something like this, where we have the initial concentration of E minus EST times, for the S term, we rearrange this, and this becomes initial concentration of S minus the concentration of S bound to the enzyme, which is the enzyme substrate complex. Okay? And then, so what happens is that you have to multiply this out, and this becomes a quadratic equation. And this can be solved analytically. But typically, in practice, that's a lot of math, and two, that also complicates our experiment. And so typically, that's not what we do. So instead, we use a trick in order to make the math simpler. And the way we do that is we use what's called pseudo first order conditions. So, in pseudo first order conditions, let's try this instead. Turn that off, wipe it down. No, this one. So pseudo first order conditions we can change the relative concentrations of, in this case, the enzyme and the substrate versus each other, so that the final equation looks more like a second order, or excuse me, more like a first order rate equation instead of a second order. And we can do that by either making enzyme much greater, the initial concentration of enzyme, I should say, much greater than the initial concentration of substrate, or we can do the opposite, where the initial concentration of substrate is much greater than the initial concentration of enzyme. In practice, it's typically much easier to do this because enzyme is usually hard to get a hold of, but substrate is a little bit easier to get a hold of. So typically we set up our reactions so that substrate has a much larger concentration than E naught. And what that effectively does is that, what that means is that the substrate concentration, if it's much greater than the amount of enzyme, then the amount of enzyme-substrate complex has very little effect on, basically an almost negligible effect on the concentration of S in any given time t. And so what that means is that this cancels out, and S naught, the initial concentration of S, is equal to the concentration of S at any given time t. And so that helps our math a lot more. And what we do, and I should also say in practice, what this means is that the substrate concentration is going to be greater than or equal to 10 times the amount of the initial enzyme concentration. Okay? And so that's typically how we would set up our, to determine the rate constant, is that, for instance, if we have 1 micromolar of enzyme, then we would have to have at least 1 millimolar of substrate, 10 micromolar of substrate or up in order to be in pseudo first order conditions. Okay? So when we do that, what we find is our math simplifies a lot. And then we can say K times the initial concentration of E minus the concentration of ES at any given time t. And again, this is a constant, okay? We know what this is because we set this up in our experiment. And S of t just becomes, from this equation, S naught. Again, this is experimentally controlled. So now when we multiply this out, it's no longer a quadratic equation. And so what the final equation ends up looking like for this is, marker's dead, ES of t is equal to E naught times 1 E to the negative K times the substrate concentration times T. And so in this way, you can see that you have an exponent on the right-hand side equal to the concentration of enzyme substrate complex at any given time t, and this takes the form that looks more like a first-order rate equation rather than a second-order rate equation that we looked at in the last video. And so we can use this, and if we plot the formation of the enzyme substrate complex versus T, then we can find out what the rate constant is from that graph.